Welcome back, this is Jeff here. After the last video, I realized that I've only briefly touched on Looking Glass so far here. Previous videos on this channel have just shown off the technology. They haven't actually explained what it is and what the need for it is. A lot of people have come back with feedback since it came out and a lot of comments as to why and what's the point. Well, I'm going to try and explain to you that, starting at the basics. A lot of you might already understand a lot of this and have experience with virtual machines and what they are and how they work. But I'm going to assume a fairly rudimentary knowledge as to what they are, and assume that you have, if you've ever used them, been either through cloud hosting, through renting an instance, say on Amazon, AWS, or on something like VirtualBox. Personally, I use virtual machines for various reasons. I actually run a company doing server management and monitoring and so forth, and for my own infrastructure for security, it makes a lot of sense to separate a lot of things up, to isolate them. So I have systems for monitoring servers, for managing servers, for retaining server information, services for email, for DNS and so on, and these are all sort of segregated up. So if any one system is compromised, a bug in, say, the mail server allows someone into the mail servers, it doesn't allow them into the rest of the infrastructure, so it sort of isolates things. Now that's the corporate view of virtual machines and how they're useful in an enterprise environment. But for you and me, you're probably thinking, well, at home they're sort of useless, or okay, yay, I can run Linux on Windows and I can play with a Linux machine, or vice versa. When it comes to anything that's a bit quicker though, or that needs more performance, like say 3D applications, say CAD or gaming, virtual machines are a bit too slow in the past. That was up until the advent of a technology called IOMMU. This was originally brought into virtual machines for the enterprise industry. It wasn't brought in for home consumer users, but those of us that are in this industry recognize fairly quickly that it would be useful for other things as well. As you might know, machines in the cloud need a lot of throughput. They need low latency, high speed, high performance connectivity to remote systems. For example, people trying to load a web page. The slowest part of that in the past was the Ethernet device, because we were emulating an actual Ethernet device. And a way around that was, or still is in some cases, depends on what kind of goals you're trying to accomplish, is to give a physical, real network device to the virtual machine to use directly. That means it's dedicated to the virtual machine. Instead of the virtual machine having to go through a layer of emulation and abstraction, the virtual machine directly talks to the hardware. And that was great. Like, we get great performance out of it, you get great throughput and really low latency. So really handy for that kind of circumstance. But not too long after that sort of came around, some of us started to realize the same technology could be applied to a graphics adapter. And for many years it was possible, but it was hit and miss. Like, it would work with some of the ATI cards back when they were still ATI, now they're AMD of course. And it would work with some of the NVIDIA cards, it would work with some of the Intel cards. It was really hit and miss, and then when it did work, it was sort of unstable, it was never great. And that was because the IOMMU extensions didn't do enough. They didn't extend out everything that was needed in order to wrap these cards up for isolated use. Other issues were there too, such as the video card. When you first turn your computer on, it's posted by the BIOS. That means that the BIOS initializes the card and tells it to start, essentially, and then the card loads its own BIOS, its own firmware, into itself and starts up, and then the BIOS starts using it and prepares it for the operating system. The problem is, if you were to give that to a virtual machine after it's been prepared, the virtual machine is going to try and do it again. And the card's already there, prepared and ready for use. So you need a way to sort of reset the card to a state as if you'd reset the whole computer. And that didn't exist. And it's still today, the support for that isn't great, as evidenced by the Vega card. Some of them won't reset If you try to reset them, they won't come back up, and this is an ongoing outstanding problem with the Vega series. Some NVIDIA cards, like the one I've got here, the GTX 1080 Ti, it will reset, but it loses access to its firmware. And you actually, in order to work around this problem, have to provide it with a copy of its firmware. So it's still not 100%, but once they're up and running, they're rock stable. They work really well. To show how this all works, this machine you're looking at right now, this screen, is my virtual machine. It's one of 6 on the one machine. 4 of the virtual machines on this computer are doing tasks for my business. They are basically backup systems for remote services, but they're all headless. There's nothing special about them. They're not running any pass-through devices. They don't have any special configuration. They're sort of bog stock standard. The other 2 virtual machines is this one and a Windows virtual machine. Now, the special thing about these 2 virtual machines is they have physical access to real video cards that have been passed into them. If I open a terminal window on here, we're going to connect from this virtual machine to the physical machine. Now, my physical machine is headless. It doesn't have a monitor attached to it. It doesn't have a video card it can directly use. So that's what we call headless, when it has no screen, no head on it. So I'll connect to it. And if I do an LSPCI, which lists all the PCI devices in the machine, and search for VGA devices, you'll see there's only 2 in the machine. We've got the Vega 10 XT and we've got the GeForce 1080 Ti. These 2 cards aren't in use here. If we list the detailed information on either one, it doesn't matter which, we'll do an LSPCI on that one and show the verbose information. You'll see down here, kernel driver in use, VFIO PCI, but we also have support for the AMD GPU, but it's not in use. AMD GPU is the actual video driver for that card. Instead, we're using this. Now, this is a kernel driver that allows you to pass through a physical device to a virtual machine, and this sort of just wraps the card up in its support so that it can be handed into a virtual machine. It doesn't actually do anything to the card other than sort of pass through memory access and pass through hardware access with a bit of bounds checking for security and various other things. It'll also reset the card if the card can do it. This card supports it according to what it tells you here, but it actually doesn't work properly. We actually have to sort of stop this card resetting. Like I was saying before, there are some quirks. When the virtual machine starts up now, instead of having an emulated card like you normally would do in a virtual machine that you want to have some sort of graphical interface on, instead of giving it a virtual card, we're giving it this card, a physical card. So when the virtual machine boots up, it initializes this card as if it owns it. The virtual machine's BIOS, in our case, we're using a UEFI BIOS called OVMF. It sees the video card, it loads its firmware and posts the card and gets it ready for use. Then it loads the operating system. In this case, it's Debian, which you can see here. What happens is, because it's using a physical video card, the card's expecting it's going to be used in a normal sense. It's actually expecting a monitor to be connected to it. And in this instance, it is. I have 4 monitors connected to it. I've got 3 lower, 1 top center. You guys can only see my center monitor, which I'm using for this recording. But it sees all the monitors and it treats them as if they're native. And it's great. Like, we get great performance out of it. If I run just something simple for example's sake, our own GLX gears, you'll see I have full 3D acceleration. Now, for some reason, the people that write OVS have decided that they're going to capture it as fast as the GPU can go, which is a bit silly in my opinion. Sorry, not capture, they render the output at as fast as they can go. Like, they don't have any sort of cap on the frame rate, so it's chewing up a lot of GPU time, which is why that's a little bit jerky. Without OVS running, it runs fine. So anyway, my point is, we have 3D acceleration inside the virtual machine, and if I list the PCI devices here, you can see this is a virtual machine. You can see the QEMU root port there, all these Red Hat devices, the virtual SCSI device for the hard disk, virtual network device, etc. This device here into VM shared memory, we'll come back to that later. That's an important device to do with Looking Glass. But then we'll see down here, the physical video card is here. So this virtual machine is using that physical card. This is where it gets a bit tricky. I also have the Windows virtual machine running, and I want to be able to remote control it from Linux. I don't want to have to switch my monitors around. I don't have a switch box to do that. A lot of people do. A lot of people just have two inputs on their screen and they can plug both cards into the same monitor and then they press a button on the screen and switch between them. And that works, and it works well. But I don't have that. And also, I don't really want to do that. I want to be more flexible in how I work. I want to be able to sort of minimize Windows down into a corner and keep an eye on it if I'm doing something that isn't gaming. Say, I do a bit of reverse engineering of Windows binaries sometimes, and I'll want to run like IDA in it or something, at which point I don't want to be restricted in what I'm doing. I don't want to be using a switch box all the time. I don't want to sort of have to switch my mouse and keyboard between machines and have it respond funny. So that's where Looking Glass comes in. Now, because Windows is doing the same thing here at Linux is doing, it expects, like I said, physical monitors attached. But we can cheat a little bit. What Looking Glass does is it is essentially a screen capture application. It's like OBS. It's recording the rendered output from the card. And for most cards, later we'll be supporting some vendor-specific APIs like NVIDIA Frame Buffer capture and so on. But for the moment, what we're doing is we're using the Microsoft DXGI Desktop Duplication API. Now, the Desktop Duplication API is great. It's actually very quick. It's not as quick as we would like it to be because we're starting to have trouble with certain things that happen if the card's a bit loaded up. We're seeing a bit of latency there. We don't always get the frame early enough if you've got a lot of post-processing effects, but basically what we're doing is we're capturing the frame. But the trick is getting that captured frame from one virtual machine either back to the host where we can display it if you're in a more conventional setup, or in my case, we want to get the frame from the one virtual machine into another virtual machine. The whole point of virtual machines is to isolate them. They shouldn't generally talk directly to each other. It's a real security feature that they can't talk to each other. But in this instance, we actually do want to share some data, and we want to share a fair amount of data. It's in the megabytes per frame. And we want to share it fast. And the fastest way to share data on a computer is through memory. We also want to do it without copying the memory over and over again, because each memory copy adds time. And like I said, we need to do this as fast as possible. Under Linux there is, or in Windows too, there is a technology called shared memory. Sorry, I'll actually correct that. It's not just a Windows and Linux technology. It's actually a general computing technology to share memory between either processors or between kernel drivers and user space applications. There's different types and methods of sharing memory. Now, when I say share memory, it's not like one program can have access to it and then it's got to give it back and then another program can have access to the same memory. It's literally they can access the same memory at the same time. And that can be dangerous because you get occurrences where they'll both try to update the same bit of data in that shared memory at the same time, and there has to be some interlocking to prevent that. But that's getting into a different topic. So that's where this device comes in, this inter-VM shared memory. This was originally written, I don't remember who by. If you want, you can look into the QEMU documentation. There's actually a text file there somewhere of the original author of this thing. I think there's also a video on YouTube where they first demonstrated this when it was in its infancy. It was for a company that wanted a proprietary networking stack for some edge routing stuff, again for networking. It was faster. Instead of emulating a virtual network device to talk between virtual machines, they found it was faster to share some memory, not between processors, but between virtual machines. And in order to do that, they created this shared memory device. But this is a generic device. It doesn't have to be just used for networking. It's literally just a block of memory that can be shared between multiple virtual machines. It can be 1, 2, or 50 virtual machines. It doesn't matter how many, as long as the way you're using it supports what you're trying to do. So if we look at the detail of this device and verbose, you'll see here we have 2 memory ranges. Now, according to these are actual PCI memory ranges. These aren't like in normal accessible memory, but they are addressable ranges. According to the IVSHMEM documentation, or into VM shared memory by QEMU, the first range is the configuration registers. It's basically how we can flag for interrupts, and there's various things we can do there. But the second range, they call that bar 2, base address register 2. Actually, I think it's 0 index, so this would be base address register 1. But anyway, you can see here its size is 128 meg. The other one's only 256 bytes, but this is 128 meg. That's user specified. I actually have told the virtual machine to add this device, or QEMU to add this virtual device to this virtual machine of 128 meg in size. That's plenty large enough for huge screens. I've made it larger than it really needs to be, simply so that I can do experimentation. Looking Glass usually needs a buffer, probably no more than 64 meg at most, but even still, you can see there we've got 128 meg. Now, we can't access that directly because that's a physical, well, it's not physical, it's a virtual device, but the virtual machine thinks it's a physical attached piece of hardware. So to access that memory, we need to involve the kernel. And for that, there is a kernel driver both for Windows and for Linux. There's a Linux one I wrote that's part of Looking Glass, and it's in the I believe the modules directory in the project. And that exposes the device for use to Looking Glass. And all that does is it maps that memory into place so that Looking Glass can access it. It doesn't do anything else. It's actually a pretty dumb driver. I think the actual core of it's only like 5 or 6 lines long. It's very simple. In Windows, we need to do the same thing. Windows sees this as a physical device as well. And initially Windows will actually say this is a unknown RAM device or something. I can't remember exactly what it is, but it just treats it as if it's part of the system it doesn't know how to handle. And just hides it under system devices. And if you follow the Looking Glass setup guide, it actually tells you what it is and how to set it up properly. So because this was built for initially networking, a driver for Windows was never written for this. It's been around for a long time, but there was never really a use case where someone wanted to tie Windows into it. Until I started playing with this. Now, it's been a pipe dream to have Windows in a virtual machine for many reasons for me. Mainly work and games, like I said before, but also I don't trust Windows. It's prone to problems. It is prone to viruses. It is prone to crashing out at the worst time. It is prone to forced updates by Microsoft that break it or make it start sending telemetry off like Windows 10 does. I don't trust it. This is my personal opinion. I know there's a lot of people out there that adamantly support Microsoft and Windows, and I got no issue with you, but personally, I don't trust it. So I put it in its own container, which is a virtual machine. The pipe dream was to be able to do that and use it for high performance graphics. And until recently, that hasn't been possible. At some point, I upgraded my PC to the Ryzen 7 when it came out. It was my first upgrade in many years, and I thought, great, we'll upgrade to that. And then I discovered that PCI pass-through works. You can actually pass a video card into the virtual machine. And it works. It was brilliant. I thought, great, we're done. This has solved all my problems. even before Looking Glass had even become a thought of how I would do this. But as I played with it, I discovered it had this limitation of needing monitors attached, and the issue now was getting the data back from the guest machine to the host machine and displaying it on the host. So it wasn't ideal. It was great. It was much better than I had before with the dual boot, but it wasn't ideal. It could be better. And I got a proof of concept working where I literally had it rendering ASCII art of the Windows desktop, sort of huge and horrible. And I remember showing it to my daughter, and she sort of cackled at how stupid it looked, this thing. But the proof was there. I had it copying the data from one to the other. At the same time, Wendell of Level 1 Techs, so excited about the MPT fix, went and made a video demonstrating it and showing, I believe it was GTA running at full frame rates on a Ryzen system with NPT enabled. It was big news. And in his video, he mentioned that the next step is to capture the frame buffer and bring it back to the host. And I had to laugh. It was just funny that he's mentioning that that's the next step, and here I am with a prototype in my hands that was already doing it. So I got in contact with him and worked with him in order to make this a reality and to publicize it. Now, Wendell was great. He did a lot of testing, got the community involved for me. It's still mostly my work, but I've got to give credit to Wendell for how much publicity he got to this project and the funding he was able to direct my way in order to get the hardware needed to fix some issues on the Threadripper platform with the Vega card. There's still issues we're fixing today and nutting down, and none of that would have happened without Wendell's involvement in this. So a huge thanks to Wendell. So back onto Looking Glass and how it's functioning. When we capture that block of memory, which is the screen, we copy it. There is a copy involved, and we copy it from the video card into the shared memory block. That copy into the shared memory doesn't need to be copied again. It just turns up wherever it's shared. It's instant. There's sort of no extra process involved because they're both seeing the same physical blocks of memory. In the client, on the guest or on the host, wherever you want to display it, it's able to read that frame out and stick it on the screen. And that's what the client application does. The advantage to this is, like I said before, you don't need a switch box. You don't need a special monitor with more than one input. You can have your mouse synchronized with everything. So let's launch Looking Glass. That's in Projects, Looking Glass Client. I've got a build sitting here. Just a forewarning, this build is a prototype. It's got changes in it that are not yet in the Git repository, experimental changes. So it actually has a lot of debugging turned on and a lot of extra stuff in it that will slow it down a bit. But for the most part, it's working great. So we'll just launch it without any arguments, and it should launch in a window. There we go. That's a bug in the build I've got right now to do with the initialization on the first connection. So you can see now there's our Windows machine. What's important here is it's in a window in Linux. That's one VM seeing the video output of another VM. And if I move my mouse in between, you'll see, we'll get rid of that. You'll see this here is synchronizing beautifully. We get nice interaction. If I pull that out into a separate window, we can scale that, whatever, and there's our Windows machine inside Linux. This is the ultimate goal. Now, you've probably seen this before, like we could do this already using Spice or VNC and stuff. But what Spice and VNC cannot do is 3D acceleration. This is where it gets interesting. So I run up 3D Mark here. There's an update. We don't really need to do an update for this test though, or this example, and we'll just run the TimeSpy demo. In the past, you wouldn't have even tried to do this. It would crash out saying there's no 3D acceleration support. Can it switch this into full screen as well? So there you go, we're working natively. And so you understand as well, I'm actually running multiple monitors, so I'm actually able to move my cursor out to another screen and work on both the virtual machine and my other virtual machine at the same time seamless, and they don't interact with each other, they don't interfere. And because I've isolated CPU cores from each machine, I can load one up 100% and it won't affect the other virtual machine's performance. But there you go. Now, like I said before, OBS is interfering with the capture rates here. For some reason they don't use VSync or whatever, but another problem for another day. When running without OBS, this is smooth, it's fluid. But there you go, 3D acceleration in a virtual machine, from a virtual machine to another virtual machine. So we'll stop this. There is a virtual device on this machine as well. Again, you can see here it thinks it's a Threadripper, etc. This is obviously a virtual machine. If we expand it, say disk drives, you can see the QEMU virtual hard disk. But you'll see down here in system devices, we have this IVSH-MEM device. That's the virtual shared memory Red Hat device that you saw in Linux. With the same block of memory, if we go into the details on the resources on this, you'll see memory range. And if you do the math, that there is the second range we saw before, and that's exactly 128 megabytes in size. So same deal, we're looking at the same memory in both VMs. Now, the downside to this, for a security point of view, it is a vulnerability, or a potential vulnerability. You now have a block of memory that is able to talk to another virtual machine and they could corrupt each other. There is a way for a bug to be exploited between virtual machines, because you're now allowing two machines to talk to each other through basically a raw interface. So work has gone into preventing that, but at this point, because Looking Glass is alpha software, it's not a concern, because this kind of a setup isn't going to really be used commercially, and probably won't ever be used commercially to my knowledge unless someone is willing to invest a lot into this. And to be honest, if they were, I'd be surprised, because it makes more sense commercially to use the SR-IOV technology that is available from AMD and NVIDIA in their professional cards, which allows a physical card to be divided up and given to virtual machines directly and pass its video feed back directly. It doesn't need any of this extra software running. Now, Looking Glass on the Windows machine, you'll see there's actually a Looking Glass host.exe. That's actually the host that's sending the data back. And you see it using almost no memory. It doesn't do much at all. It's just taking a capture and dumping it into that block of memory and setting a few flags to say, hey, there's more there's another frame here. It also captures the cursor and the cursor updates and the shape updates and stuff like that, so that it's rendered. Because this cursor, while it looks like it's on the virtual machine, it's actually rendered locally using OpenGL. It just knows where the cursor is and what the picture for the cursor should be, and so it renders it locally. And we do that for performance reasons. So we'll close that out. But that's Looking Glass. So the possibilities of Looking Glass are quite astounding. But it requires time and effort and a lot of work to make it function. And a lot of this time and effort goes into performance tuning. So much new features at this point, we're now just tuning for performance and trying to make it as compatible as we can. Anyway, I hope that that's given you a good rundown on what Looking Glass is, on how virtual machines in general are being used, and also where all these technologies come from and why it's taken so long to get to this point. And I hope this video has been informative in a way that's understandable, and I apologize if it's hard to follow. As I said in my previous videos, these are my first ever videos as far as YouTube's concerned, and first attempt I've had at educating people on maths like this and demonstrating software like this on a technical level. Anyway, my name's Jeff, and thank you for watching.